I'm your host, Dr. D. Welcome to Math in the House. Today, we're doing Math Analysis, Chapter 7, Section 4, Part 2 of Vector Applications and the Dot Product. I'm your host, Dr. D. Vector projections. Now this is similar to the component, except it's a vector instead of a scalar quantity. So the projection of u along v, the projection of u along v, or I should say the projection of vector u along v. Like I said, that's similar to the component of u along v, except the projection is a vector itself. So let's take a look at it. We have vector u and vector v. Now the composition, the component of u along v is just that yellow distance right there. But the projection of u along v, so we drop our perpendicular down, and now we have a vector that starts from the tail of u and v and goes to the place where the perpendicular gets dropped down. That is a vector, and it's entitled projection of vector u on v. Now, projection of vector u on v has the same magnitude as the component of vector u on v, and it has the same direction as vector v. So we have our magnitude and direction of this projection.
Bam! Do we have that in a Christian school?
That's annoying. Hold on. We know that the component of u along v is the magnitude of u times cosine of the angle. So the projection of u along v is going to be the component of u along v times vector v divided by the magnitude of vector v. Now, vector v, any vector divided by its magnitude gives you a unit vector. So, we take the projection of u equals the component of u along v, which is the magnitude of u times cosine of the angle times vector v over the magnitude. So what do we have here? Well, we have vector v times cosine of theta times the magnitude of u over the magnitude of v. So what's in this yellow box is one way of showing the projection of u onto v, is just saying it's vector v times cosine theta, and that's the angle between u and v, times the ratio of the magnitudes of vector u and vector v. Now, there's another way of showing what projection of u along v is, and that is, let's take u dot v. So let's take vector u dot vector v. Well, we know that that's the magnitude of u times the magnitude of v times cosine theta. Well, the component of u along v is the magnitude of u cosine theta. So basically, u dot v is just going to be the magnitude of v times the component of u along v. And so what I can do is divide both sides by the magnitude of vector v, and what I have is the component of u along v is u dot v divided by the magnitude of v. All right, so we go on down to here then. The projection of u along v is u dot v. Let's see, okay, here's what I'm doing. I'm starting with this equation right here. So projection of u along v equals the component of u along v, which is u dot v over magnitude of v, times vector v over the magnitude of vector v. So I'm basically taking this equation and substituting in the component of u along v, and so what I have then is, notice on the bottom I have the magnitude of v squared. On the top I just have u dot v, and then I have vector v. Now, so if you look at this thing, and this is the main definition of the projection of u along v, you have u dot v, which is a scalar quantity, divided by the magnitude of v squared, which is also a scalar quantity. So this whole thing in parentheses is all just a plain number. Now vector v is a vector, so it's a number times a vector, which makes a vector, which is what we were saying in the first place, that the component of u along v is a scalar quantity, a plain number, but the projection of u along v is a vector quantity because it's u dot v over the magnitude of v squared times vector v. So this all looks really complicated. The thing is, if you really memorize this yellow box, it becomes pretty simple. Let's try an example. Find the projection of u along v. So u is 4, 3, and v is 6, negative 1. So notice u is 4, 3, and v is 6, negative 1. So I want the projection of u along v. So notice that's the purple vector right there. All right, so we don't know theta, so this would be a more convenient property or more convenient expression to use. If we did know theta, then this would be simpler. But since we don't know theta, but we do know vector u and vector v and the magnitude, this is the simpler one to use. Okay, so the projection of u along v, oh, and I should put, projection of u along v is u dot v over the magnitude of v squared times vector v. Well, let's just crank that out. So u dot v means take u and v, multiply the x's, 4 times 6. Then multiply the y's, 3 times negative 1. So 24 plus negative 3 is 21. So u dot v is 21, a scalar quantity. Now the magnitude of v, well, I just take v and I square the x, square the y, add them up, take square root. 36 plus 1 is 37, square root of 37 is the magnitude of vector v. Well, the magnitude squared is just going to be plain 37. All right, so the projection of u along v is 21 over 37, the dot product divided by the square of the magnitude, times vector v, and vector v is just 6, -1. That's it, piece of cake. You could distribute this, although you don't have to. But if we distribute it, 21 times 6 is 126, so 126 over 37, -21 over 37. So that basically shows what we see in the purple right here, that it's still a 6-to-1 ratio, 6 right, 1 down, because it's in line with vector v, but it's only 21/37 of vector v, which is a little more than half of vector v. So, piece of cake. Now, since we know that the projection of u along v we can resolve vector u into orthogonal components. What's orthogonal components? Those are vectors perpendicular to each other. The word orthogonal means perpendicular. Now, normally, we're interested in resolving a vector into its horizontal and vertical components, into its x and y. But in this case, we're interested in resolving it into components that are going to be parallel to vector v and perpendicular to vector v. So here's what I'm talking about. Vector u is right here, the blue. Now, vector v is the red. Now, what I'm interested in doing is making a component of vector u that's along vector v and a component of vector u that's perpendicular to vector v. So notice, here's basically what used to be horizontal and vertical is now along v and perpendicular to v. So, the projection of u along v is my parallel vector, and the orthogonal vector is going to be the vector that's perpendicular to v, which is u sub 2. Now, vector u equals vector u sub 1 plus vector u sub 2. In other words, if I take vector u sub 1 and add vector u sub 2, I end up at vector u. So, u sub 1 is the projection of u along v, and u sub 2 is going to equal u minus u sub 1. All right, so let's see what that does with numbers. So u is 2/8, or I should say u are 2/8. Okay, u is 2/8 and v is 8/6. So notice u is the blue, 2/8, and v, which is the red, 8/6. We want to resolve u into u sub 1 and u sub 2, where u sub 1 is parallel to v and u sub 2 is perpendicular to v. In other words, u sub 1 is the projection of u onto v, and u sub 2 is the vector that goes from v perpendicular up to u. All right, so we're experts at this now. U sub 1 is the projection of u onto v, which means it's the dot product of u and v divided by the magnitude of v squared times vector v. Okay, so let's crank that out. So we have the dot product, which is the product of the x's. 2 times 8 is 16. Product of the y's. 8 times 6 is 48. 16 plus 48 is 64, and dividing by the magnitude of v squared. Well, v is 8/6, So the magnitude is 8 squared plus 6 squared. Take square root of the whole thing. So 64 plus 36 is 100. Square root of 100 is 10. 10 squared is magnitude of v squared. Times vector v, which is 8, 6. So 16 and 48, 64 over 100 times 8, 6. Well, 64 times 8 is 2 to the 6th times 2 to the 3rd is 2 to the 9th, which is 512, divided by 100, which is 5.12. And 64 times 6 is 384, divided by 100, 3.84. So my projection of u onto v is 5.12, 3.84. And that's my u sub 1. Now, u sub 2 is going to equal u minus u sub 1. Well, u is 2, 8, and I'm subtracting 5.12, 3.84. So I just go 2 minus 5.12, and I get negative 3.12. And 8 minus 3.84 is 4.16. So that means the u sub 2 vector is 3.12 to the left and 4.16 up. So 3.12 to the left, 4.16 up. Now, to verify that u sub 1 is parallel to vector v, which it should be, I'm going to check the slopes of both of them. Well, the slope of u sub 1 is y over x, 3.84 over 5.12, which ends up being 0.75, 3/4. And the slope of vector v is 6 divided by 8, which is also 0.75. So the slopes are equal, so vector u sub 1 is parallel to vector v, just as we had hoped. And now to verify that vector u sub 2 is perpendicular to vector v, the dot products have to equal 0. Now that's an important point we hadn't discussed yet, and that is the dot product of two vectors equals 0 as long as those two vectors are perpendicular. So I do the dot product of u sub 2 and v, so I go x times x plus y times y, and that does end up being 0. So everybody goes home happy. All right, cruising onward. Projectile motion. This is a subject that you will get in any physics class, high school or college. It's the first thing you'll get in college physics. X is the distance in the horizontal direction. Y is the distance in the vertical direction. Now we have a projectile that's traveling through the air. And so the projectile will always be traveling along a parabolic arc, a parabola. Now that's one thing that's highly important in the education of children and puppies. They need to understand parabolic motion. If your kid can't catch a ball, or your puppy can't catch a ball, you just got to send it back. So it's important. You fathers and mothers need to teach your children about parabolic motion so they won't be ridiculed when they get to school. All right, parabolic motion. First thing, we look at our x distance. Well, x equals the magnitude of velocity times cosine of the angle times time. Well, let's look at magnitude of velocity. That's just your velocity times cosine of the angle. Well, that's your x distance. So basically, what we're saying is distance equals rate times time. Distance equals rate times time. We've had that since Algebra 1. Okay, now, the y is similar. You have the y distance equals the y rate times the time. But we also have this thing called gravity that keeps it from going up. Without gravity, things would just continue up at velocity times sine theta. But we have gravity that's pulling it downward at 1/2 times the acceleration of gravity times time squared. Now, gravity in the United States of America is 32.174 feet per second squared in the USA. And gravity is also 9.807 meters per second squared in France? I just love that. Okay, so gravity, 32.174 feet per second squared, or 9.81 meters per second squared. In your physics class, that's what you're going to learn, but you need to know both for here and for college. Okay, so one other thing we need to remember is the y direction, positive is up and negative is down. The x direction, generally right is positive and left is negative. So that's why you see minus 1/2 gt squared, because gravity is pulling downward.
Bam! Do we have that in a Christian school?
That's annoying. Hold on. A batter hits a baseball at a 30-degree angle with the horizontal, with initial velocity of 150 feet per second. How far will the ball travel? Okay, so we know that x equals the velocity times cosine of the angle times time. 150 cosine 30 times time. Problem is, we're asked how far will the ball travel. That's what x is. How far will it travel? Well, how do we know what x is when we don't know what t is? We don't know how far it will travel until we know how long it travels. Well, how do we know how long a ball will travel? Well, it will travel as long as it will stay up. See, if you're on the moon, that ball will travel further because the gravitational attraction is less on the moon than it is here on Earth. If you're on Jupiter, the ball won't travel nearly as far because gravitational attraction is greater. So the whole thing that causes a ball to stop traveling forward is the fact that it gets sucked back down to the planet. All right, so we need to look at the y direction to know how long the ball will travel. So the y distance is 150 sine 30 again. That's velocity times sine of the angle times time minus 1/2 g t squared. Now g, remember 32.174 feet per second squared. We're given velocity in feet per second, so we know we need to use g in feet per second squared. So when the ball lands, its height is 0 feet because it's on the ground. So we're going to let y equal 0 and then solve for t. In other words, we're going to find out how long it took until it got back down to the ground. So I'm going to plug in 0 for y. So 150 sine 30 times t minus 1/2 times 32.174 times t squared equals y, which equals 0. So now I just have an equation with one variable, and that's time. If I multiply 150 times sine 30, I get 75t minus half of 32.174 is 16.087 t squared. Notice I have an equation with a t and a t squared. So what I'm going to do is just factor out a t from both of these, and I have t times 75 minus 16.087t equals 0. Okay, so that means either t equals 0 or what's in the parentheses equals 0. And if 75 minus 16.087t equals 0, then that means t equals 75 divided by 16.087, which is 4.66 seconds. Now we know how long it's been up, so we can find out how far it's gone. So we go back to the x equation, and I go 150 cosine 30 times 4.66 seconds, and I'm going to get 605.6 feet. So clearly, that ball's a home run in any ballpark in the country. So, that's it. Baseball game is over. Have fun with these.